Great, thanks, Peter. And happy to be with everybody, virtually coming at you from the California coast, thousands of miles away. So today we're going to talk about scaling your architecture with services and events. And as Peter said, I've spent a bunch of time as an engineering leader at eBay, at Google. I'm at eBay again right now as the chief architect. And I also led engineering at Stitch Fix and was a VP of engineering at WeWork. And a bunch of the stories and sort of lessons that we're going to talk about today come from a bunch of these experiences. So I want to talk about four different things. First, I want to talk about the kind of architecture as your kind of product and company evolves, like what kind of architecture should you have at your different phases of development? And then we're going to focus in on when it's appropriate to have a service architecture. We'll talk about a lot of details around there, what it looks like to migrate from a monolithic architecture into services. Then we're going to spend a little bit of time talking about event-driven communication. And then finally, we're going to spend most of the talk, the remaining part of the talk, combining services and events together as tools in our architectural toolbox to do some really interesting things. So let's start by talking about architecture evolution. And I like to think about the phases of a company or product growth in sort of these in these areas. So when we're starting out as a product or as a company, we probably have a single team. We probably all fit around a conference table, at least when we're able to be all together in the same room safely. We want to optimize for rapid iteration because maybe we haven't even found product market fit. Maybe we haven't even found our business model yet. And typically, the appropriate architecture for this phase of development is absolutely monolithic. So, I'm not a believer that people should anywhere start with microservices or any aspect of a distributed system. But over time, you will have found that product market fit. You'll have engaged your initial customers, and you'll really start hopefully scaling. And so now you've grown to many teams, not just one. Now, instead of rapid iteration, we're adding in the requirements to have a lot more velocity and a lot more scalability about the software that we build. And then here's when it's more appropriate for us to start introducing a monolithic or a microservice architecture instead of monolith. And then nothing continues up forever, so everything's always an S curve. So, in the twilight years of your company or your product, you're in what I'll call the optimizing phase, where maybe we'll start to consolidate down from many teams to fewer teams. Rather than velocity and scalability, you're thinking about efficiency and sustainability. And then you're probably consolidating your architecture into something smaller. What I want to focus on today is this scaling phase in the center. But the thing I want to be super clear on is maybe 1% of the applications on the planet are in this scaling phase. And you can imagine that they're the people that you'd think, the Googles, the Netflixes, the Amazons, the eBays of the world. So I want to make we're going to talk a lot about microservices. We're going to talk a lot about events, but I'm really talking about this phase of development of a company, not starting out. So let's explore some of the examples of those companies that are now big that started off really small. So eBay, where I work again today, is on maybe, depending on how you count, its fifth complete rewrite of its infrastructure. So it started out famously almost exactly 25 years ago when the founder Pierre Omidyar took a 3-day Labor Day weekend and built the first thing in a monolithic Perl application on his little, probably 386 tower under his desk, and built the first thing that ultimately became eBay. And he was trying out in 1995 this new cool thing called the web. The next iteration of eBay was a monolithic C++ monster. It grew to 3.4 million lines of code in a single ISAPI DLL. So that was pretty horrible. They were actually hitting compiler limits on the number of methods per class, which I'm horrified to say that I actually know that, at least at the time, you could only have 16,000 or 16K more precisely methods in a class, and they were actually hitting that limit. The next iteration was a breaking it up of that monolith into, I wouldn't call it microservices, but maybe mini applications. So maybe several hundred individual Java applications, one that was maybe for the selling part of the site, for the search part of the site, for the buying part, et cetera. And then now it's fair to characterize eBay as a polyglot set of microservices. Twitter has gone through a similar evolution. So you maybe call it on its third generation. It started famously as the world's largest Ruby on Rails application, which I love the fact that they codenamed that the monorail. The next iteration was breaking out the front end mostly into JavaScript, the back end out into services mostly written in Scala. And now it's fair to characterize Twitter as a polyglot set of microservices. Amazon has gone through a similar evolution. So when it started out in 1995, it was a monolithic front and Perl C hybrid front end, monolithic C back end. They spent most of the years 2000 to 2005, breaking up that monolith into a service-oriented architecture, which we would now call microservices. A lot of those services then written in Java and C++. And now it's fair to call Amazon a polyglot set of microservices. So it sounds like there's a pattern here. But the pattern has two elements to it, or actually three. One is no one starts with microservices. Past a certain scale, almost everybody ends up with something or co-evolve to something that we now call microservices. But again, I want to caution a lot of companies, maybe most companies, never reach that scale that requires that. So given that kind of background, I'd like to take a little deeper dive into what it means to have a service architecture and what we get out of it and what are some of the issues there. So again, let's think about the problem that we're trying to solve. We're trying to solve not just a technology problem, but also an organizational problem. So, in our growing organization, we don't just have one team, we have a bunch of different teams. Again, if you were early eBay, you'd have the buying team and the selling team and a bunch of other individual teams, and they all need to be able to make very rapid changes independently of each other. So what you want is for the architecture of the system to sort of mirror or be a dual of the organizational architecture. So where we have one domain, we should probably have one team, and then that one team should build and maintain one or maybe a small number of services. And I'm sure a bunch of us here are familiar with Conway's Law, which is the idea that our organization is reflected or should be reflected in our architecture. In fact, the law itself is that you can't help but ship your org chart, that your organization is almost naturally going to get reflected in the architecture that you build. So with services, where we give the ability for those individual teams to have to be autonomous from each other and also be accountable end to end for the capabilities that they write. So teams are able to independently design, develop, deploy, and operate their individual services. And then ideally, service teams are going to own their services end to end all the way along. The other thing that we're getting out of this service architecture at this phase is abstraction and encapsulation, which is a great thing in software engineering in general, but particularly appropriate when we're building a large-scale system like this. So that service boundary is giving us fault isolation. So within that service boundary, we're able to catch and hopefully deal with issues that come up, errors that come up. It's also a boundary within which we can make good performance optimizations behind that interface that we expose to the outside world. And then particularly in the modern world, and I think less widely appreciated as it should be, it's actually a security boundary. So if you're doing any kind of regulated stuff, anything with payments or anything with people's personal information, being able to isolate parts of the system where we deal with financial information or private information, for example, separate from other things, it allows us to have put more stringent operating requirements around those areas that again deal with financial or private information. And then, what I have found over and over again is a critical aspect to making one of these service or architectures work is to have a really strict discipline around that interface boundary. So we want to make sure that we have a really well specified interface contract. And then because we have that contract, we can leverage that to build tests that test that component separately, and we can mock out the other services that this service integrates with. And as I'm sure most of us know, one of the great tools that lots of people use is Pact, which is, of course, an Australian original thing. And then the last thing I want to point out here is the importance of using that publish service interface as the only mechanism that gets data into or out of the service. And one thing that was a huge problem in eBay about 12 years ago was before they went to a fuller, a more more correct service architecture, people were able to kind of have backdoor access to databases. So you would, people would use services, but they were also able to like read and write directly from databases. And as you can imagine, if I'm able to read and write your data from behind your back, what kind of service, what kind of operating guarantees can you make in your service? Basically none, because again, I'm able to do things behind your back. So where we are with this is we want to have an architecture where we have services that are single purpose. They have a simple, well-defined interface that we've negotiated with our customer teams. They're modular and independent. And then critically to that last point I was talking about is they have isolated persistence. So we don't share the database for one service with another service. So now I want to talk a little bit about how do we get to this service architecture. So how do we get from a monolithic, say, database to a more service-oriented architecture where we have separate databases? And I'll use a specific set of examples from when I worked at Stitch Fix. So Stitch Fix, if you're not familiar with it, is a clothing retailer. At the time that I worked there, almost all of Stitch Fix's data lived in a monolithic shared database that was used by a lot of different applications. So the problem was that if that database was down or slow, the entire site and the entire company would go down. So our problem here was that we wanted to decouple applications and services from that shared database. So let's see how that would work. And I'm going to try to make it a little bit simpler diagrammatically by imagining that there are only 2 applications and only 3 tables. And as a practical matter, there were 80 applications and services and 175 tables, but that's way too many lines to have on a diagram. So let's imagine that there's just an application that where people choose the clothes that we're going to send to our customers called styling. And then there's a warehouse application where we maintain the inventory in our warehouses, and that they're each using these common tables around clients, around SKUs, and around items and inventory. So the first thing that we want to do is we want to create a service, a service interface around the client, the client object. And then what we want to make sure is that instead of having those 2 applications use the client table in the database, instead they access client information through the service. And so when I arrived at Stitch Fix, we had done a bunch of these things. So I said, hey, how are we on our service migration? Oh, great. Well, we have all these services and applications are using the services. And then I asked, well, but did we remove actually the tables from the shared database? Oh, no, we didn't get there. So we're nowhere near done yet. And in fact, if we stop at this point, we're worse off than if we hadn't started at all, because we have all the problems of a distributed system between these applications talking to services, and we have all the problems of a shared database, and we have none of the benefits that we want to get that we just talked about from microservices. So please, 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 if you're breaking up your monolithic database, don't stop at this phase. Keep on moving. So what keeping on moving means is that we move that table out from that shared database into what I'll call a private database that's associated only with this particular service. And then we'll do the same thing for items. We'll do the same thing for SKUs. And then we'll just keep continuing on and keep pulling out pieces of the monolithic database into these separate databases. And I want to be super clear that these are the service boundaries, right? The service boundary is not just the code that we have in the service. It also includes the data in the database. And then again, as we said before, there should be no way to get to the database except through the published service interface. So now we've talked a little bit about service architecture. Now I want to move on a little bit and talk about event-driven communication. And then again, just as a telegraph, we're going to use what we learned about services and about events and combine them together to do some really interesting things in the last section. So in terms of events, those services, when the state changes around an item, around a user or something like that, we want to publish an event that other parts of the system can then react to. And the best way I have found to think about an event in one of these systems is an event is a statement that something interesting occurred. So item purchased, user upgraded, something like that. And so different, the consumer services and consumer applications in the system are going to subscribe to that event. And then the critical component for me is that we want to make sure that events are a first-class entity in our system. And so for any of those services, So the service interface doesn't just include, the synchronous request response front door that's, REST and JSON or gRPC or something like that. But the service interface also includes all the events that that service consumes and all the events that that service produces for others to consume. And why are we doing this? We're doing this because we want to be able to decouple those separate domains and teams from each other, that we give them a well-defined interface for them to interact with one another, and they can actually interact with each other asynchronously. So that allows us to decouple the producer services that are producing one of the events from the consumer services. And so they have what I'll call decoupled availability, where the producing service can be up or down and the consuming service can still work, and vice versa. So the producer can be producing events even if the consumer service is down. And we can also scale them independently, which has really nice properties as you get to large scale. And then the last thing, very much just like in the service aspect, is we want to make sure that we have a really strict interface discipline around those events. So just like we had a well-specified service interface, we want to have a well-specified event schema, which again allows us to test event production and event consumption separately, and also mock out the other part of that interaction. Okay. So now that we've got sort of the basics out of the way of services and events, let's combine them together in interesting ways. So the first thing I want to talk about is leveraging the idea that the service, at any interesting piece of data in our system, whether it's about items or about users or something like that, should be owned by one and only one service. And that service is going to be what I'll call the canonical system of record for that data. So in this example, let's imagine we maintain customer data. So we're going to have a customer service which owns the customer information. But as you can imagine, there are tons of places around a system like Stitch Fix or a system like eBay where we need to know information about customers. So the way I like to think about that in large scale is the customer information is owned by the customer service, but then we produce events that are then consumed by all the other services that need customer information. And those events that we have produced as state changes produce copies of the customer information in other places. But every one of those other copies is a read-only, non-authoritative cache. And every one of those words is important. It's read-only. So if I want to update customer data, I should be going to the customer service rather than doing it somewhere else. And it's non-authoritative, meaning that the billing system or the styling system might be slightly stale or out of date from the information that's in the customer service. And anybody who's familiar with DNS knows this is exactly how the DNS system works globally. So the other thing I want to talk about is a producing service, making sure that it doesn't that it produces that when it changes its own state, that it produces an event or it doesn't. Like it either changes its state and produces the event, or it does not change its state and does not produce the event. And there are two ways that I've seen that be done very effectively at large scale. So the first way to do it is called change data capture. So how that works is the producer system is going to write its update or insert its new object into its local database. That database is going to write a change to its transaction log, whether it's the bin log for MySQL or something like that. And then we'll have a connector like Debezium or Kafka Connect or something like that, that's sitting there tailing that transactional log of the database and then sending the event. And again, the problem that we're trying to solve here is we want to make sure that anytime we update the database that we guarantee that we're also going to send the event. So this is one approach, this change data capture. This works in a lot of situations, but often this can be a little bit low level. So another common model is what's called the transactional outbox. So instead, in this model, the producer is going to write its state changes in its normal, table for users or items or something like that. And then it would also potentially write to an outbox, which I'll call an event table in that same database. And that will queue up all the events that need to be produced. And then that service or another service would be looking in that event table to make sure that those events ultimately or eventually get delivered. And so again, that would allow us to make sure that we have updated the state of our item or user or something like that, and that we guarantee at least eventually to have produced the event that other people can then listen to. So The next interesting combination we're going to talk about is how we can use services and events in a microservices ecosystem to deal with shared data. So when we were in that nice, safe, comfortable, monolithic world, that monolithic database made it really easy to have shared data between the different parts of our system. We just simply created a new table that other parts of the system could use and join to. But where does shared data go in the microservices world, right? We've broken everything up, and so there's no one database for us to put the shared data in. So two options here that I've seen work effectively. So the first, which is pretty straightforward and simple, is just simply looking it up synchronously whenever we need the information. So in this particular example, let's imagine that we have a fulfillment service, which is going to send packages out through the physical mail to people that arrive at their doorstep. And that fulfillment service is going to need to know the current address of Michelle or Peter, let's say. And so a perfectly legitimate approach is for the fulfillment service to ask the customer service in real time, what's Michelle's address or what's Peter's address, so that it can send there. But this might not, this is a legitimate approach, but it might not have the operational characteristics we like. Maybe where it takes too long for the customer service to respond with somebody's address. So there's a latency issue. Or maybe there's an availability issue because we're putting a lot of load on the customer service and it's not able to keep up with all the requests from the fulfillment service. Or maybe we just simply want to have the fulfillment service operate when the customer service is not available. So if any of those things are true, we can use a slightly more complicated approach that leverages events. So I'll call this option asynchronous event and a local cache. So how this works is the customer service still is the canonical owner of customer data. That doesn't change. But what happens is the customer service will send what I'll call an address updated event whenever Michelle's address updates or is changed, or Peter's address changes whenever somebody moves house, for example. And that fulfillment service is going to cache the current customer address for those people, and then we can ask the fulfillment service to send packages, and the fulfillment service always has the updated customer address. Cool. So that's how we can leverage events to solve some of the problems that we introduce in the microservices ecosystem around shared data. So now let's talk a little bit of how we can do joins. So again, in a monolithic database, it's really easy to join tables together. So we just, modify our SQL statement. So we'll say, select from A, inner join B on some join condition, and then we have our join super easy. But again, if the one half of the join and the other half of the join are living in different services and therefore in different databases, we really don't have this option in the microservices world. So splitting the data between those microservices makes joins more complicated. So again, we have a couple of options about how to tackle this problem. So the first way to do it is, again, simply, join the two parts of it in real time. So let's imagine that we want to show our customer an order history page. So all of the orders that she has made with us. So we're gonna need to go over to the customer service and get some information about her, and then we're going to need to go over to the order service, and using her customer ID, we're going to need to find all the orders that she's made with us in the last while. So again, super simple. So we're going to get the customer from one side, query the matching orders on the other side, join it in real time in the client application. And by the way, this is basically every web page on the planet, right? So this is every web page where you have more than one request that fills in details on the page. So, but again, maybe it's too maybe operationally it takes too long to join these things in real time. Maybe it would put too much pressure on the customer service or on the order service to do this all the time. So maybe there are operational reasons why we don't want to do this in real time. So now we have the second option, which is a service that's going to be what I'll call materializes the view. So in this example, I'm giving a slightly different example where let's imagine in the Stitch Fix case where we have a bunch of items in our inventory and we want to hear about people's feedback. When we send them that particular item, we want to remember whether they liked it or not. But the way that we currently get feedback is, we send them a box and with 5 items in it. And so we get those kind of things in bulk. So what we ultimately want to do here is we want to join together the items with the feedback that we got at order level. So the way that we can do that is we're listening to events that come from the item service. We're listening to another set of events that come from the order service. And we're maintaining a denormalized join of items and orders together in local storage that's associated with this new item feedback service that represents the join. And so we've basically materialized the view here. And so now we can make queries to the item feedback service directly, and we're not joining it in real time. December 2020 asterisk here, in AWS reInvent last week, they introduced some new interesting service that does this, which I think is called AWS Glue Elastic Views or something like that. So, maybe you actually don't even have to write a service, but the concept is the same, where you're getting updates from one side of the join, you're getting updates from the other side of the join, and essentially materializing the view and using that. So if that sounds weird and hard, I want to kind of disabuse you of that notion, because there are tons of common systems that we use every day that materialize joins in this way. So, I'm using the term materialized view very intentionally, because lots of enterprise-y database systems, by which I mean the ones that you pay for, have this concept of materialized view. Most NoSQL systems actually are asking you to do joins. So if you use Cassandra or React or Voldemort or one of the NoSQL systems, typically those systems are asking you to materialize views ahead of time to make things a little bit more painful on the write side, but make things a lot easier to do on the read side. Any search engine on the planet is essentially a materialized view of lots of different things all joined together. And then again, any analytic system on the planet is a join of lots of data from lots of different places. So even if you don't think that you're doing the technique that I just talked about, you probably are somewhere in your somewhere in your company. Okay. So the last interesting thing I want to solve here with services and events is transactions. So in a monolithic database, it makes transactions across multiple entities really easy. So we could construct this transaction where we begin it, we do some inserts into table A, we do some updates to table B, and then we either commit or roll back. And that happens in this nice, beautiful ACID way. So it either all happens all together or it doesn't happen at all. But once we've split, A into one service and B into another service, and they're in different databases, doing transactions like this is really challenging. And so you might think that the strategy would be, well, I've heard of these things called distributed transactions. Maybe we should do that. So Pat Helland, who's one of my favorite, great thinkers and thought leaders in our industry, wrote this wonderful paper in 2007 called Life After Distributed Transactions, an Apostate's Opinion. And the reason why he's an apostate, that's like a heretic, is he spent most of his career, 20 years or so, building distributed transactions and transactional systems in SQL Server and Tandem and so on. Anyway, so what he says is, what he learned over time trying to do this at large scale is, in general, application developers do not implement large scale applications with distributed transactions. And Pat, being very clever, said that even more concisely. He says grown-ups don't use distributed transactions. All right, well, what do grown-ups do? They do it this way. So instead of thinking about it as an ACID transaction, think about modeling that thing that we wanted to do all in one go as a workflow or something that we'll call a saga. So let's take that transaction and think about it as a state machine of individual atomic events. So let's re-implement this thing, like I say, as a workflow. So let's imagine that we update we change or update service A, that's going to produce an event, which is then consumed by service B. It's going to do some updates locally, produce one or more events that are then consumed by C. And so you have this chain of, where you wanted to originally like update A and B and C all together, you do it more as a workflow. And so you might be looking at this and saying, yeah, but what if something goes wrong? How do we deal with that? So we deal with that through compensating operations in reverse. So we do the equivalent of a rollback, by undoing our operations in the reverse order. So maybe we get to C and we realize that we want to, not continue this workflow. We want to make it go back to the beginning. So we would, in reverse, produce some events. B would undo its stuff. We might produce some more events, and A would undo its stuff. So again, this might sound a little bit complicated and a little bit overmuch, but I'm going to disabuse you of that notion that this is actually a very natural fit for lots of problems that we deal with every day. So there are tons of real world systems where the straightforward modeling of the domain is exactly a workflow. So let's take the example of payment processing. So let's imagine that I wanted to pay Peter 100 Australian dollars. And so what one would like to have happen is I agree to pay him that, and it is immediately and atomically extracted from my account and shows up in his account. As everybody probably knows, that is not how it works any place on the planet. Instead, there's a whole bunch of complicated events that go back and forth between my bank and his bank. And, if you live in the backward US, it takes 3 days for that to happen. So, that's not good. But the payment processing itself is an actual workflow. Expense approval. So I would love to be visiting you physically instead of virtually. And if I had done that, I'd probably accumulate some expenses because I'd, be having some wonderful food in Australia. And so I would, when I got back to California, I would try to get those expenses approved and get reimbursed for them. And again, there's a workflow there, right? So, I submit my expenses, it goes up my management chain, my boss approves it, and then her boss approves it, et cetera, or doesn't. And then it comes back down. But again, it doesn't happen atomically in a transactional way. The other, maybe the most striking example of where things are a workflow is the actual software development process itself, the stuff that most of us are actually doing day to day in our jobs. So if we were all physically together in a room, I would ask everybody to raise their hand if whenever you were finished building something in your IDE, when you hit return in your IDE, that it immediately and atomically was deployed to production. And if we were all together, nobody would raise her hand because literally no software development works that way. So instead, as we well know, we run a bunch of code. Hopefully, we're writing and running tests locally. We've accumulated a bunch of changes. We commit those changes. They get code reviewed by one of our colleagues. They get merged. They enter a pipeline where they get tested further, that they get deployed to production, et cetera. But there's this whole, again, workflow or series of events that happens that starts on my laptop and ends up somewhere else. So whenever I talk to developers that are kind of new to these ideas and they say, well, Randy, I can't possibly visualize in my head this idea of, this eventual consistency idea where one part of the system has, one view of the world and another part of the system has another view of the world. And I ask them to think about what they do every day, right? Because of course, the natural state of events is that if there's version 10 of our code, running in our service on the site, I am working on version 11 or version 12 or something like that locally. And so that's not something that we have any difficulty dealing with. So, sometimes we need to expand our brain a little bit. Cool. So many real world systems use workflows and sagas to solve these problems. But what you'll also notice about these systems, which is different from that ACID transaction situation, is that we're able to observe intermediate states. So you can observe the fact that I have attempted to pay Peter 100 Australian dollars, but they have not actually, they've not actually gotten to Peter. So there's this intermediate state there where that payment is pending. So the huge problem is if we try to hide that intermediate state. So I strongly recommend that part of that well-defined interface that we're going to create for our service is that we embrace these intermediate states, we model them explicitly, and we expose them in our interface because it's part of the domain, it's part of our model. So in the payment example, we're going to model a payment could be started, a payment might be pending, and then ultimately the payment is complete. And then for expenses, again, as I mentioned, again, it's a set of intermediate states. So we're going to model an expense is submitted, an expense is approved or rejected, and expense is ultimately paid, which, by the way, will then kick off one of those payment workflows that we just talked about. For the software development process example, again, a feature or a commit might be being developed, it might be reviewed, it might be deployed, it might be released if we're using something like feature flags. We deploy it separately from releasing it. So again, this idea of modeling and embracing the intermediate states in our interface is a really good practice. Cool. So I had mentioned in the abstract that I wanted to talk about how serverless fits in here. So if you think about how the transactional workflows or these sagas that we're talking about, they are simple event-driven processing. They have very lightweight logic. They are stateless, and they're triggered by an event. So this is almost the definition of a great application for something like Lambda or Google Cloud Functions or Azure Functions, because as one of these stages in the workflow, they're very simple and they're very easily modeled by something in serverless. So this is a great opportunity if people are still in 2020 trying to figure out maybe what serverless is good for. Like, I think it's good for a lot of things, but this is one thing that it's very obviously a great match for. Okay, so we did a quick whirlwind tour. We talked about the architecture evolution over time. We started with the starting phase. We talked about the scaling phase. We talked about the optimizing phase. We talked about some best practices around service architecture. We talked about how to do event-driven communication. And then we spent a bunch of time using these two architectural tools that we now have in our toolbox, the tools of services and events, combining them together to do some really interesting things. So thank you very much. This was a lot of fun for me. And I think we can do some questions.